We've talked a lot about this electronic or electric interaction between charges and the intermediary of the electric field. And some of us are still confusing the electric field with the electric force. Okay? We found two, count them, two different ways to create an electric field. If we have a point source, then that field, again, the field is the force that would act if I had a +1 coulomb being pushed on it. Okay? That electric field is going to be away from the positive source and towards the negative source, and it's going to be given, the magnitude will be given by Coulomb's law, the KQS over R squared. Now, the second way that we found to create an electric field was with a sheet of charge of surface charge density sigma, where sigma is just the total charge divided by the area. It's how thick I smeared on the charge. In 1 unit of area, 1 meter by 1 meter, how much charge did I get in there? Now, in that case, we found that the electric field didn't depend on how far we were away from the sheet. And that was surprising to some of us. Now, regardless of how you got the E field, whether you got it from a point source or a sheet of charge or multiple sheets of charge, you can always put that E field in here and multiply by the test charge to get the thing that you really care about. This is always the last step here. What you really care about is the push or the pull, the tug on that test charge. And we do that through this equation here. Okay, only 3 equations so far. Now, folks, we're moving on. On Friday, we're going to start talking about voltage. And my experience is that many of you, some of you, are still confused about electric force and electric field. And some of you are tempted to just put it off and say, you know, I'll figure it out before the midterm. I'll figure it out over spring break on the beach. Okay? That's what you want to be doing on the beach. Folks, if you don't have a handle on electric field and electric force, the 4 lectures on voltage starting on Friday are going to just seem like a mystery. They're just going to be a waste of your time. So you need to get this handled now. You can't put it off. Let's look at this problem that you voted off the island. It was an old exam problem. It proved challenging. You have 2 sources here. You have a point source that's governed by Coulomb's law. You have a large sheet of charge. That's the word you look for, is large sheet of charge that is governed by this formula on the right. We are told that if we put an electron at that x, which is equal distance between the two, 20 centimeters from each, if we put an electron there, it experiences no electric field. It experiences no electric field because there's no electric field there to experience. I could have put anything there and it would have experienced no electric field. Now, I know that the electric field at the x, due to that point source, is away from the point source because it's a positive source. The field is away, and it's given by Coulomb's law. So if I plug in to Coulomb's law here, I would get 9 times 10 to the 9 times 3 times 10 to the minus 6 over 0.2, that's 20 centimeters squared, and that's going to give me 675,000 newtons for each coulomb. Okay? Oh, that's a big field. But if I put an electron at the x, it experiences no net electric field. And that's because that charged sheet has to cancel out the field due to the point source. So that immediately tells you whether this is a positive or a negative sheet. Which is it?
Positive.
Positive, because the field is away from the sheet. Now, in this part of the problem, they asked us to find the sigma, the surface charge density. Well, I know that if this one is 675,000 newtons for each coulomb, this one has to be 675,000 newtons for each coulomb. And so if I use this formula here, my E is my 675,000, and that's going to give me my sigma. It's positive sigma, so I don't need the absolute value sign, over 2 times 8.85 times 10 to the minus 12. Okay, and so I solve for sigma just by multiplying that out, and I get, let's see, that's not doing very good, so I get 1.2 times 10 to the minus 5 coulombs per meter squared. Okay? How are we doing, folks? That's okay? Now, here's where things get rough.
I think that was just a turn.
We take a neutral metal block and we put it just a little bit to the right of that sheet. Now, it's neutral. It has just as many positive charges as negative, but it's metal. We're going to talk about conductors today, but we already know that in a conductor, the electrons are free to move to their happy place. And with all of this positive charge in this sheet, and I've got that positive charge over there, I got a whole bunch of positive charge to the left of the metal. That's going to cause the electrons to swim left, and that's going to leave naked protons on the right. Now, if I look at the X, at the location of the X, there are now 4 contributions to the total field. I have a contribution due to this point source that's that big. I have a contribution due to this sheet, which is that big. But I also have contributions due to these charges, and this is not a big sheet of charge, this is just a small block. So I would consider this to be more like a point source than a sheet, a large infinite sheet. And so here, distance matters. And so when I put my 2 contributions up there, I've got an E field towards the negative charge and an E field away from the positive charge. This field has to be smaller than that field. Why? Because these sources are further away from the X than these are. Now, what I want at the X is the total field. And I know that these 2 cancel, but these 2 do not. And so that means the total field is going to be to the right. Yes, sir?
Since it's an electron, can we assume that it's a negative point charge?
Yes, that's my question.
The definition of the electric field was fixed before even I was born. It is the force that would be exerted if I put a +1 coulomb there. If they ask for the field, that's what they're asking for, and it's to the right. Now, if I put an electron there, the push, the electric force, the actual tug that you feel, which way would it point? To the left. And that's because with the field to the right and the negative electron, the force is going to be in the negative right direction or the left direction. Now, some of you have not quite figured out that the charge on an electron is just a number. You're treating that like a variable. How do I calculate the charge on the electron? No. the charge on the electron is minus 1.6 times 10 to the minus 19 coulombs. That's how God made them. They're that charged, okay? And that number will be on the front page of the exam. Now the charge on a proton is the elementary charge, is just plus 1.6 times 10 to the minus 19 coulombs. So don't be solving for those charges, they're constants. Okay, questions about this problem here? Aren't you glad it's not going to be on your exam? Okay. I just want to talk briefly about this third page of the tutorial. I understand that some of you were given some incorrect information during the tutorial. I apologize. I try to train my teaching staff. Not all of my teaching staff can get to my meetings, and so sometimes we have problems. Let me remind you what we've got here. We've got two charges, A and B. These charges are insulating balls that have been charged up by rubbing, and they've been glued to the table. Now those two things are important. It's got to be a non-conducting ball that's charged, and it's got to be glued to the table. And the reason that that's important is that we're going to bring a third charge, C, into the room. And we don't want our problem to change as the day goes on. We want it to stay the same problem. Now think about what would happen if these balls that were charged were metal balls. You know, finite sized metal ball. When I bring in that ball C, that's going to cause the electrons on the metal ball to swim away or swim towards, depending on what C is. Okay? That's going to change the problem. Now I've got to glue these charges down to the table, because if I didn't, it's possible that bringing in ball C is going to make them fly off the table, and that's going to change the problem. So it's important that they are non-conductors and that they are glued down. Now here's the gist of that third page. A student is confused. The student says, I have these two sources, A and B, glued down to the table. I wanted to explore, to investigate the field in A and B with a third charge C. But as soon as I brought charge C into the room, I changed the field in the room, so I can't make a measurement. Now clearly, this student is confused. Now, the reason that we can use ball C is that when you bring ball C in the room, this is what the total field looks like in the room. But this is not, I repeat, this is not the field that C experiences. This is not what C sees. C is only pushed by everything that's not C. Ooh, that sounds bad. That sounds like World War II. Not C. Too soon. So, I didn't see that coming either. Now, sometimes they just pop out. Now, C does not push electrically on itself. So the electric field that is pushing on C is the field due to A and B. And so this is what it experiences. If you put ball C there, if it's positive, it'll be kicked that way. If you put ball C there, it'll be kicked that way. If you put ball C there, it'll be kicked that way. Now, this is the field that would be experienced by a fourth charge, a charge D that was brought into the room. Because every charge is pushed by everybody else. Not themselves, everybody else. Okay? So when I bring in ball C, A and B are the Klingons that make the field. C is the Captain Kirk that is experiencing the field. When I bring in a charge D, Charge D is the Klingon that's testing the Captain Kirk that's testing the field, and A, B, and C are creating the field. The field is created by everything that's not being pushed by it. Now, in some of the tutorials, some of our staff were saying, oh, well, C can be used because we make C a very small charge so that it won't affect the field much. That's just bogus. That's just, I mean, if you bring in a charge C and you're expecting to use this field, you have no idea what direction that's being pushed. Not with this picture. It can be pushed any direction. That's not what C experiences. This is what C experiences. And it doesn't matter whether C is huge or small, it doesn't push on itself. Okay? Check that your neighbor understood that, and then they got the right experience in the tutorial. I usually try to get through the day without a Nazi joke. That was unfortunate. That was unfortunate.
It's been a long time.
Okay. And before we go on, I've been to Dachau 4 times in my life. I know that we don't joke about Nazis, so I apologize if I offended anyone. Okay. We found that for a sheet of charge, we have this formula here, where the charge density, sigma, is just the total charge divided by the area. And epsilon naught is 8.85 times 10 to the minus 12. It's just a number. It's called the permittivity of free space. We find, therefore, that the electric field is the same at each of those x's. If it's 5 newtons for each coulomb here, it's exactly 5 newtons for each coulomb there. The spacing between the field lines gives us the strength of the field, and the spacing is the same. Now, typically, the more common problem is 2 parallel plates, one positive and one negative. That's the more common problem because we typically charge plates by stealing electrons from one of them and putting it on the other. And for every electron I steal from the first plate, I leave a naked proton behind. And so these 2 plates get charged up, positive and negative, with the same magnitude of charge. Now, if I look at the field between those plates in this typical situation, and remember, this green line represents a plate that comes out over your head. And so the same with the purple plate. I get a contribution away from the positive and towards the negative. And those are the same size, regardless of how far I am away from the plates, as long as they're infinite plates. Now, if I look there, I get 2 contributions, one from the positive, one from the negative, exactly the same size as the first. And I can do that anywhere between the plates. Now, if I look outside the plates, away from the positive is down, and towards the negative is still up. And they're the same size contribution if the charge densities are the same size. And so that means I get 0 field outside. Now, the way I would represent this with field lines, I'm trying to represent that there's no electric field out here. I do that with no field lines. I'm trying to represent that the field in between the plates points up and is everywhere the same magnitude. I do that by putting the lines parallel to each other. Okay? Now, this is a very, very useful device. In many of our laboratory experiments, we would like a uniform electric field that stays the same value throughout a certain region of space. And we don't want an electric field outside of that region messing with the rest of our electronics. And so we use parallel plates to achieve that goal. Now, the size of that E field is given just by looking at the contributions. each of these contributions comes from a single sheet that follows that equation. And so I have two contributions. If we call this an apple pie, sigma over epsilon naught, I have half an apple pie and half an apple pie, and that gives me one apple pie. And this is why we defined epsilon naught the way we did. We left this 2 in this equation for a single sheet. We could have just defined epsilon naught to be twice what it is. But the more common situation is the situation of, I'm going to put it over here so that you can see it. The electric field due to 2 sheets, and that's going to be sigma, well, that's not a vector, I'm sorry, but it is positive or negative. This is a vector. Now, this formula can sometimes get misused. On the exam, I might put 2 sheets, one that has a positive 2 sigma naught, and one that's got a negative 3 sigma naught. And what I find is that many people will just blindly plug into that formula. Well, it's 2 sheets, I counted 2. 1, 2. Okay? No. This is for 2 sheets that have equal but opposite surface charge density. Okay? So this is only going to be valid for the case where I have a plus sigma and a minus sigma. If the charge density is not the same on the positive and the negative, you can't use that formula. What would you do with a problem like this? You've got one for homework. Superposition. Yeah, you treat each of these as if they were a single sheet. You add up the contributions just like we did here. Okay. Now, outside the field is 0. Let's see how well we understood what we just learned. I have 2 infinite sheets, insulating material that's been charged up by rubbing. This line represents a sheet that divides a class in half. Joseph got cut in half back there. Okay? This line represents a sheet that goes over your heads. It just kind of keeps on going. Now, if I look along the 45-degree axis there, at point 1, and I ask you which of those vectors, A, B, or C, represents the direction of the electric field due to these 2 sheets, what would you answer? This may be our best chance of everyone getting a right answer.
Oh, you think I picked E? You think I'm that person? Oh, no. I can't be.
Turns out I can prove it.
Really?
Yeah.
Oh. Okay. What?
Okay.
We have riding on that. 5 extra credit points.
Okay.
Count me in.
Excellent.
People.
Yeah, we're not going to Disney World because of these 2 people. Okay.
Do you have a clicker in your pocket?
That would be fun. Okay. We use symmetry, and that just, that had to be the answer. It had the same symmetry as the problem. And remember, symmetry is summed up by this cartoon. One day, Greg, I'll be sitting at that desk. If you can't tell the difference between left and right, then the answer is going to look the same, left and right. Okay? Now, let's try something more challenging. Suppose I looked at point 2, which is down there, and asked you which of these 3 directions, A, B, or C, is more close to the actual direction of the electric field at point 2. With your clicker now, Pascal. Oh, now we divide up the class. Okay? It's either going to be B or it's going to be C. Well, let's use superposition. Okay, that's the way we solve these types of problems. If I look at the contribution from that horizontal sheet, it's a positive sheet, so the contribution will be away, which would be up. And I've drawn that arrow some arbitrary length. Now, if I look at the contribution due to the vertical sheet, again, it's a positive sheet, and it's going to give me a contribution away or to the left. But the question is, how big should that contribution be compared to the one I had before? The same. The key is that that formula doesn't depend on distance. It's independent of how far you are away from the sheet, and so I would get the same contribution, only to the left. And with those two contributions, I see that the only answer that's possible is B. So check that your neighbor put B and help them out. Okay. Folks, let's start our discussion of conductors. This purple bar represents a plate of metal that's coming out towards you. Now we know that in a metal, electrons are free to flow. And this next part I can't prove without teaching you about Gauss's law, and I've tried year after year to go there, and it takes too much time, and I don't get all the way to home base. So you're going to have to trust me on this. I hate saying that, but this is one of the few times I will. The electrons in a metal very quickly get to their happy place and stop. They get to what we call equilibrium in 10 to the minus 16 seconds. Now see if you can blink in 10 to the minus 16 seconds. No, you were too slow. You're way too slow. Okay? So, if you're patient enough to wait 10 to the minus 16 seconds, no matter how you started out, the electrons will all be in their happy place. Now suppose I just dump a great big bucket of electrons onto that metal. Well, they're not happy there. You know they're not happy there. And so they want to get away from each other, and they're going to end up on the surface, on both surfaces. Now if I call sigma naught the total charge over the area of that plate, then each of those sides is going to get half of that sigma. Right? Half the electrons went to the left, half went to the right. Now if I look at an electric field, the total electric field inside the metal, and it doesn't matter where I look inside the metal, I picked a location dead center, but it wouldn't have to be. I have two contributions. I have a contribution to this due to this negative sheet that is to the left towards the negative. And the size of that is given by this formula for a single sheet of charge. If I look at the contribution due to the charge on the right, it's the same size, but in the opposite direction, towards the negative. And I get an E field inside the metal that is 0. And that's the bottom line. The E field inside of a metal, if you wait 1 times 10 to the negative 16 seconds, is always going to be 0. If it were not 0, I mean, these are just the excess electrons that I threw on that metal. But the metal has billions and billions of electrons. If the electric field were not zero inside that metal, electrons would still be flowing. And what we find is that after 10 to the minus 16 seconds, they're in their happy place stopped. Now, this is true not just for this symmetric case, but for any metal of any shape. You could have a metal statue of some war hero, and everywhere inside that metal, your electric field has to be zero. Now, we call this electromagnetic shielding. Now, we know that electric field lines are born on positive charge and they die on negative charge. And so that means if I have a neutral metal ball, I'm going to have electrons swim over to this side in between these plates so that they can kill the electric field lines. I have just as many positive charges over here giving birth to field lines so that they can continue on. But inside the metal, there would be no field lines because there's no field. Now there's a second characteristic of this shielding, and that is that electrons are free to move around the surface of a metal. So if I had an electric field that had a tangential component, if part of the electric field was tangent to the surface, it would push electrons, and electrons would still be moving. They would still be trying to get to their happy place. So that means that once the electrons are in their happy place in equilibrium, all electric fields have to come into that metal at 90 degrees. Now this has very important consequences when we get to lightning rods next week. We'll find that this single principle determines why lightning rods have to be sharp. Okay? Now, on the 4th floor of Cobley Hall nearby, we have a space electronics laboratory, and in that laboratory they build satellites, okay, CubeSats. And after they're done making their satellite, the last thing they do is they wrap it in aluminum foil. Everything in there is wrapped in aluminum foil. Indeed, if you go to NASA, it seems like NASA has spent more on aluminum foil than anything else, because everything's wrapped in aluminum foil. And that's to essentially shield out electric fields from outside the box. Okay? You don't want electric fields from outer space interfering with the electronics inside your box. Was there a question over here? Yes, sir.
I was just wondering if that's why you could hide in the trash can during the lightning storm?
Yes, it's exactly why. We call that a Faraday cage, and that's what we're going to talk about right now. Okay, in order to demonstrate this, I first of all have to demonstrate an electroscope. Now, a simple electroscope just has pieces of foil that are hanging. And when I put a charge on the electroscope, some of that charge spreads out to the foil, and then the foil is repelled from each other, and you can detect the presence of the charge. My electroscope is a little bit more complicated. It's made up of this metal ball here that's connected by metal to this vertical bar. Now that vertical bar contains a second little bar that's free to rotate. Now this outer metal is just structural support. It's not part of the device. And you can see that it's not connected to the metal bar or the metal post because there's plexiglass top and bottom here insulating it from this circular metal. Now, if I take a rubber rod and I charge it up with a simulated rabbit fur, first of all, remember that this is an insulator. This is not a conductor. And so when I charge this up by putting extra electrons on it, the electrons are stuck where I put them. And so if I just touch the metal ball with this, all I do is transfer those electrons that were right at the location where I touched the ball. And you see that it didn't have very much effect. If I want to transfer more charge to that electroscope, I've got to scrape it off the rod like it were peanut butter. Okay? And that gives all the electrons a chance to jump ship. And now you see that the vertical rod and the rod that's free to rotate are repelling each other, and so I get something that indicates that there's charge. Okay, has everyone had a chance to see that? Okay. Now to neutralize this, I just touch it to a very large conductor. Well, I'm a very large conductor, and so I neutralize it. Now, what we're going to do is we're going to start with a neutral can, and we're going to dump a bunch of electrons in this can with this Wimshurst machine. Now the Wimshurst machine is a way of separating negative charge from positive charge through a process called induction that we'll talk about towards the end of the semester. But suffice it to say that now I just collect electrons here, and I'm missing electrons over here, and so this rod would be negative, this rod would be positive. And if I turn the crank and collect the charge, I can build up enough charge that it actually jumps the gap. Now, Friday we'll start talking about voltage. But your gut tells you that voltage is all about fear. How afraid should I be of that? Okay? And it turns out that in order to jump a 1 centimeter gap of air, you need 30,000 volts. Okay? So we're generating a fair amount of voltage here. Now, what I'm going to do is I'm going to start with this can being neutral. I know it's neutral because I'm touching it. I can show it's neutral by taking this wand and nothing. Okay? So you keep her the wand. Okay? Now, I'm going to take this chain and hang it on the negative side and put the negative side away from the positive side so it can't jump a spark. And I'm going to turn the crank, generating electrons and dumping them into the inside of that can. And I'm going to dump a whole lot of electrons because I'm generous and they're free. So we'll just fill that can right up. Okay? Now, I'm going to use this wooden stick to take the chain and put it off there. Now, if I take my wand and touch it all around on the inside, and come over here, I get nothing. And there's a little bump from the collision, but nothing. Where'd the electrons go? On the outside. If I touch the outside, there you go. Yeah, that's the response I was looking for. Okay. And this time it stays deflected. Okay, so all the charge goes to the outside. This was first demonstrated by Michael Faraday, so it's called the Faraday Bucket. Now, we can use that Faraday Bucket idea to talk about what this gentleman brought up with lightning. If we look at lightning, there's some lightning. That lightning was on the day, the actual moment, I think, that Pope Francis was chosen. Not a relative. Not a relative. There's some lightning in Dubai. How many of you have been to the Boston Museum of Science? They have the most marvelous Van de Graaff generators, In truth, only one of these is a Van de Graaff generator, and the second is just a facade. But in one of these, I'm not sure which one it is, there's a giant rubber band that rolls up and down. And just like our little Van de Graaff, we spray charge on it with a metal comb, and we take the charge off at the top. And they build up huge charge distributions up there. Now, what they have here is a graduate student, because they're expendable, in a metal bird cage. And what they do is they charge up the Van de Graaff and then they lift up the bird cage until they get lightning. And the grad student demonstrates that the charge stays on the outside of the cage by putting his or her hand right on the metal bars where the lightning is striking, on the inside. Now, we used to take our kids there all the time, and there was one grad student who was more brave than the rest. And what he would do is he would put his tongue right on that bar on the inside. And I tell my kids, that's my hero. That's who you want to grow up to be. That's who you want. Now, when we're in a lightning storm and we're away from our house, the best thing we can do is crawl in a metal can, or better yet, crawl into your car. And in your car, you are protected from that lightning. Why?
Electrons like the outside.
What's that?
Electrons like the outside.
Electrons like the outside. Exactly right. Now, the more common answer that you hear is because of the rubber tires. And the rubber tires will protect you from the lightning if your rubber tires are 1 mile thick. I don't have tires like that. It turns out that it's the Faraday cage, the metal cage around you, that protects you. If you're in a Corvette, you're toast. Okay? Now, I'm going to show you a little movie. This is Richard Hammond struck by lightning.
Technology to blast a car with lightning. 2 of those places are in Holland and Germany. But only one of those nations is laid back, liberal and fun-loving enough to let me actually sit in the car whilst they hit it with 800,000 volts. Yep, it's those zany Germans. This is the Siemens High Voltage Lab in Berlin. Normally, this place builds and tests high voltage equipment for power stations and the national grid. These transformers can generate almost 2 million volts of pure electricity. But today they're going to use that electricity for something else, to make lightning. They're going to zap me and this car with 800,000 volts, which is a lot. Stuff in your house runs on 240 volts. If it hits me directly, they'll clear me away with a shovel. You might be thinking that the tyres are going to protect me by insulating the car from Earth because they're rubber. Now, if the electricity can make it from the sky to the car, it can make it from the car to the ground. What's going to protect me is this, the body shell itself. Like all cars, the new Golf's body forms a Faraday cage. And a Faraday cage is something that attracts electricity and then sends it shooting around the outside so that whatever's inside shouldn't be harmed. But the problem is, this isn't like brakes or airbags. Car firms don't test for lightning strikes, so I've no idea how it'll go. Right. My life is now in the hands of A-level physics. The lightning will come out of these transformers along the wires and then shoot down to the car. What was that?
Okay, hold on. Raise the voltage.
You're starting to raise the voltage.
The voltage is going up.
200,000 volts.
We did have a briefing with the scientists, and he said keep my hands together towards the centre of the car and away from any metal objects. But it's a car. It's made of that.
400,000 volts.
Just don't stick your hand out the
No,
window.
it doesn't.
600,000 volt.
It's really buzzing there. I don't know what's coming from the gas panel. The battery on that, it's building, it really is building. It builds a tension with it. It's quite strange. You can almost feel the tension. My hands are buzzing. Oh, when I was doing stuff for my car, I've got error up on the dashboard. Handbrake light flashing. So it works. Assuming I'm not now talking to you with wings and a half. I'm alive. What assuming is the car. The electric windows work, obviously. Lights, they work. Stereo, it's nice.
Car's name is Fritz.
Indicators, I mean everything. And it starts. It still works. Amazing.
Okay, we'll talk about voltage on Friday.